some more paperwork we have to do.
Okay,
later,
awesome.
So,
Great.
okay, so sorry everybody for all the drama. It's okay. Yeah, so welcome to Lynn Pocher's dissertation defense. I guess I should introduce the committee. So I'm Dan Lathrop, and I'm co-advising Liam's dissertation with Patrick Pocher, far end. It's important that I point out that Professor Chris Jarzinski is the dean's representative. So if anything strange happens, then you might have to describe to the dean what. Well, but you know, we have guidance from them. And then Dr. Ruby Haber is also on the committee, and Dr. Dwight Mahagan at far end. And yeah, so Liam, do you want to proceed?
Absolutely.
Please.
Thanks so much for that introduction, Dan. It's a privilege today to talk to you today about much of the research that has composed my dissertation. I'd like to first thank my advisory committee that Dan just introduced. They have pushed me along, given me feedback, advocated for me, and are now adjudicating on the merits of the research I performed. I'd also like to thank my collaborators, who are shown here at the bottom right of this slide, whose help much of the work in this dissertation would have been able to be done. I also like to thank the funding sources for this particular research, namely the National Science Foundation, which supported the work I did at NIST, and also the Department of Energy, Office of Planetary Physics, which supported the work I did here at the University of Maryland. In this dissertation, we pose the question, what is the minimum necessary detail in measurement or data-driven modeling and simulation to capture complex electron dynamics? Here in this setting, what we're doing is integrating disciplines of experiment, numerics, and theory, 3 disciplines of physics, into a cohesive package so that we can analyze systems containing large numbers of electrons. In the first chapter of this presentation, we analyze the dynamics of a superparamagnetic tunnel junction, which is a device that creates a thermally induced bistable fluctuations, which when binarized, create random bit streams that can then be used to solve computational problems, an example of which I'll provide you in a moment. There is need to create a representative model to capture the fluctuations of these devices. And the way we do that is creating a measurement-driven, overdamped, longitudinal model, which is a one-dimensional stochastic differential equation. We then all evolve our approach in the second chapter of this presentation, not just analyzing the dynamics of one device, but an entire ensemble, a swarm of charged particles. Namely, we are analyzing the dynamics of the beam centroid motion in an electron ring here at the University of Maryland simulation. This is a particular methodology we are developing that's novel, which is underneath one of the grand challenges of my field of accelerator physics, beam prediction, which is vital to speed up accelerator design and commissioning. And we developed this novel methodology with an elementary test problem at the University of Maryland. And we derived evolution equations for the motion, the ensemble motion of this swarm of charged particles, motivated only by data. When we compare the results of the evolution equations, which are a 3-dimensional ordinary differential equation set, to a first principles model and also a machine learning technique. We then progress our approach in the third chapter, not just analyzing the ensemble dynamics of a swarm of charged particles, but the entire phase space structure of a particular distribution of charged particles in an electron beam. And what I mean by phase space is the space spanned by all the positions and velocities of a particular distribution. And the way we do that is by measuring the velocity space structure directly from experiment, which we then insert to in a simulation to analyze the dynamics of a particular electron beam, which is crucial to understanding the future beam dynamics. And we compare the results of this particular simulation to both a first principles model and other simulations initialized with ideal distributions. All of these chapters here, in sequential order, require increasing detail to capture the complex dynamics manifesting in these systems. So returning to the first chapter, I'll provide an example of a computational problem. So many problems are mathematically equivalent to the icing problem shown here at the top right of the slide, where this is a particular model for the Hamiltonian of a bunch of spins that are interacting. And it's a model for a ferromagnet, basically. You have a bunch of magnetic dipoles that are interacting with each other. And their interaction term is associated with these spins which multiply each other. It had this matrix J, which couple the various spins. In typical 1D IC problems, you only have nearest neighbor interactions. So only the main diagonal entries or right off the main diagonal entries of this particular matrix are non-zero. You then have a linear term, which is associated with an applied field, which multiplies all the various spins sigma to J. Now, a random configuration of a 1D IC model is shown here at the top of the slide, where you have a bunch of up spins and down spins, which correspond to +1 and -1 for spin sigma. These values have been binarized to this following formula here on the right-hand side of the slide. And so depending upon a particular configuration and given an interaction in an applied field, you can find the Ising Hamiltonian energy, H. This has a scalar value as a function of the configuration. One particular problem that's mappable to the Ising problem is the traveling salesman problem, or in the modern day and age, the traveling Amazon truck. So many of us in this room here probably have Amazon 2-day Prime. Now, I'd like you to just imagine that there was only one Amazon Prime truck in the entirety of the United States. Now, before you say, oh, what was us? This is only an imagination, it's a thought problem. Now, if there's only two cities this traveling Amazon Prime truck has to deliver between, Chicago, Illinois, and Washington, D.C., there's a trivial solution to this particular problem. It's a straight line. It's whatever would be the shortest distance to travel between these two cities. However, as you scale up the size of the network that this prime truck has to deliver between, for example, if you also include Seattle, San Francisco, New York, and Boston, plus many other cities, the solution to this problem to minimize the distance the truck has to travel and thus the delivery time becomes more complicated. And you can't really solve it analytically. And one way to solve this problem is to put it on a computer. So thus, this is an example of a computational problem. Now, on the bottom left of the slide, I'm showing you here the Hamiltonian for the traveling salesman problem, which I will not describe in detail, but only in broad brushstrokes. Terms on the top of this particular equation correspond to energy penalties at each city in a particular sequence that corresponds to a configuration and Ising spins appears more than once. The third term corresponds to a penalty if there's no subsequent connection between two cities in a sequence. And the last term corresponds to minimizing the distances associated with all the various cities in a sequence. And so one can quickly see that solving this particular Hamiltonian can become very quickly at the size the network scales up, analytically untrackable. And so there's a need to solve this efficiently on a computer. One way to do that is by allowing each of the spins in a particular Ising spin configuration to take on the value from a random bit string, 0, 1, and a string of random numbers, basically. And so that allows one to stochastically search the energy landscape of the Ising Hamiltonian and thus find the minimum energy, which corresponds to minimizing the distance that the traveling Amazon truck has to travel in order to find a solution. And so one way to produce a random bit string from a physical source and not using a pseudo random number generator, which is computationally inefficient, is to use a tunnel junction. So what's a tunnel junction? So a tunnel junction is a device that creates a random bit stream by binarizing the thermally induced bistable fluctuations of basically a materials pancake. So what I'm showing you here on the right-hand side of the slide is a schematic showing an illustrative representation of a tunnel junction, which, when driven with a constant current source I, has, when you measure the voltage across of it, can fluctuate between two different values. So the way this particular device works is that it has, in general, 3 different layers. One layer here on the top has a fixed magnetization, which has all the average spins associated, all the electrons or all the materials in that particular layer pointing in one particular direction. Now, all the various spins in that layer aren't pointing in that same direction. It's just an average value. There's an insulating layer whose resistance depends on the relative orientation of the average spin of the fixed layer and the free layer. And the free layer here on the bottom has an average value macro spin, which can either be aligned, which corresponds to lower energy and lower voltage, or anti-aligned with the fixed magnetization in the upper layer. And so what we do to measure these devices is measure the voltage across these nodes, basically. And the result of this measurement, I'll show you in a moment. And these particular guys, the voltage is a proxy measurement for the average spin state within this free layer. And in order to solve computational problems and use these devices as random bit streams, one way to do that is come up with models which are representative for their fluctuations, so that those models can then be used to design application-specific integrated circuits. Now, if, for example, all of us have phones in this room, right? And on that phone, there are many microchips and various other physical devices which were designed on a computer. They weren't designed in the lab with a bunch of wiring and stuff like that. And the engineers who designed those devices used models for all the circuit elements that were within that particular chip. And so designing the chips costs a lot of time and money. And if you want to solve computational problems with these devices here, using random bit streams, you can't, it's challenging to wire them up in a lab to create solutions for the dicing problem, for example. And so in order to create high fidelity models, we need to understand the dynamics of these devices. So typical macrospin models cannot capture the statistics of these devices, and macrospin models are simple, low-dimensional stochastic differential equations, which are derived from first principles. And the alternative approach are micromagnetic simulations, which solve the dynamics of this current source, I, which has a source of electrons, and these electrons also have a spin, which interact with the spin of this free layer here, and can cause it to flip between either aligned or anti-aligned when a particular sweet spot current is running through this device. And the micromagnetic simulations that resolve the detail within this free layer are too computationally expensive to be used readily for design of application-specific integrated circuits. There's a need to design compact models that are easy to use in commercial circuit simulation software. So what's a typical time trace of these devices look like? Like, what's the big if? What's the big if? So what I'm showing you here on this slide is a typical time trace of a tunnel junction. You can readily see two states, the AP state, the anti-aligned state, which has higher voltage, positive in this case, and the P state, the lower voltage case, which is shown here at the bottom. Now, the reason this voltage here is negative is because the mean has been subtracted out of the particular measurement. The barrier between the P state and the AP state is shown here in this gray dashed line. The horizontal axis of this particular plot is time in nanoseconds, and the vertical axis is voltage phi in millivolts. So what we want to do is to capture the statistics of these fluctuations. When binarized, produce 1 or 0. So what I'm showing you here on the right-hand side of the slide now is a histogram for the entire time trace of a particular sequence that was taken in the lab by some of my collaborators in France. And what you can see here at the top of the slide is histogram associated with the AP state, and then the bottom, histogram associated with P state, which is obviously parallel. And what we want to do is come up with a model that captures these statistics, because the first principles model, which is simple and compact, cannot capture the asymmetric wells of this particular histogram here. There's not enough. The statistics in that particular first principles model that are not representative of the actual physical device. Another thing we wish to capture, aside from the histogram, is the dwell time distribution. The dwell time is associated with the time the system spends in a particular state. For example, the dwell time here, for this particular instance, in the AP state, is the time that the system spends from this transition to this transition before it goes to the P state, which then spends this amount of time in the blue right here. And what we want to do is come up with a model that captures the entire distribution of the dwell times. And the way we will do that is by creating a simple 1D Langevin model, the simplest model that captures the mixed deterministic and stochastic behavior of this particular device. The Langevin model is shown here at the top left of the slide, where you have time derivative of the voltage phi equaling the deterministic part f of phi in blue plus a stochastic part GFI times the noise term, which has zero mean and also is delta correlated in time, which corresponds to white noise. We assume this noise term as well to be Gaussian distributed. The plot I'm showing you here in the bottom left is of the histogram from the prior slide that's rotated 90 degrees now. We have on the horizontal axis voltage phi in millivolts and probability per 200 microvolt bin on the vertical axis. This histogram is the Boltzmann distribution associated with this process here. And we know from statistical mechanics that the integrand of the partition function goes as e to the minus Hamiltonian. And for a long time trace, we approximate the integrand of that partition function to be the probability in state space phi for us. And when we take the negative natural log of this probability phi, we get a quartic function, which is the effective potential that this device interacts with. That's the potential I'm showing you here is shown notionally in this blue line. This is an actual potential. If you take the negative natural log of this, there's asymmetry in the wells. This is a notional representation. The system state here corresponds to this black particle dot. And there's some noise term which provides some stochastic forcing. Now, in order to create and insert these particular terms for the FFI and GFI, the deterministic and stochastic parts, we take short-term time limit statistics of the actual time trace in the device. And so what we insert for the diffusion term here, GFI, is shown here in the bottom right of the slide, where we have the diffusion coefficient shown in units of millivolts squared per nanosecond on the vertical axis, and on the horizontal axis, voltage phi in millivolts. This diffusion is associated with stochastic noise and is multiplicative, meaning it's not constant. It's a function of the state. It's varying, and that multiplies this noise term here. We then insert a drift term, which looks like if you squint, looks kind of like a cubic, and which corresponds to the force associated with potential, and is thus this blue arrow when the particle system state is at this location here. Now, the vertical axis of this particular quantity is drift in millivolts per nanosecond, inserted directly into this guy. And the horizontal axis of this plot is shared with the lower pane plot. So how does our model do? So our Langevin model replicates the Boltzmann distribution. The experimental data of that time trace I was showing you a moment ago of our device is shown here in the black dots. And then the results of the Langevin simulation are shown in the blue hollow squares. And you can see that they're right on top of each other. The gray dashed line corresponds to the barrier that we denote to be the minimum of this potential right here, which is around -1 millivolts. And it's the same barrier location we were showing before on the typical time trace slide. Now, the inset plot is showing the ratio of the simulation to the experiment. And we see for most of the data of the simulation and experiment, that ratio is going to be unity, except near the edges where there's not much data. Now, the most remarkable result of our model is its ability to also capture the dwell time distribution. Recall the dwell time corresponded to how much time the system spent in a particular state before transitioning to the next one. And what our model does is capture the entire distribution of the dwell times. So on the upper pane plot, with the horizontal axis dwell time tau in nanoseconds, but shown on a log-log scale, whose vertical axis is probability per 100 picosecond bin, we observe that the experimental data shown in the black and the gray and the simulation data shown in the blue and the yellow capture a t to the -3 halves power law distribution, which corresponds to the random walk, which we believe is associated with the random motion near this barrier here, because at this location, the force is near zero, and thus the deterministic part of the Langevin equation is zero. And thus you only have the stochastic part, which is a random motion thermal walk, acting at this particular location. And so at this location here, the particle, the system state just wanders back and forth across that barrier associated with the random walk. In addition, on the lower pane plot, which has now plotted on a semi-log scale, and the vertical axis being probability per 1 nanosecond bin, the model captures the exponential tail associated with the independent events popping off, which is associated with the system state transitioning between the two wells, P and AP and P. And that's representative of a Poisson process. So in summary, our Langevin model performs remarkably well. Its most significant result is the capturing of the dwell time distribution, which is not inserted directly into the model. Now, this particular model here is now representative and usable in circuit co-design and ASICs, which can then be used to solve computational problems. Now, in this chapter of this presentation, I've shown you the analysis that we have done to capture the complex dynamics of this one particular device. In the next chapters of this dissertation, I'll be showing you the results of us capturing dynamics of a swarm of charged particles. So a murmuration is a biological example of complex dynamics. And a murmuration is a particular structure that a flock of starlings exhibits. This describes the structure of this particular flock. Now, this is an image, which when I play is a movie. And you can see here how this structure evolves as a function of time, this flock of starlings. And what we're doing in the next chapters of this dissertation is not just analyzing the dynamics of one particular device, one bird in this flock, or one electron in our swarm of charged particles, but we're going to be examining both the center of motion, the center of mass motion of swarm, for example, and also the phase-space structure of a swarm of charged particles. So in our second chapter, we're analyzing the central dynamics of an electron beam as it propagates in an electron beam. The image I'm showing you here is of the University of Maryland electron ring, which is a mess of wires and metal. And you can see also this green line here, which is an artist's representation of the beam centroid that's like rattling around in the accelerator. Now, this is, as one of my advisors likes to say, a student-sized accelerator, and it has a diameter of around 3.6 meters or so, and a resulting circumference of 11 or 12 meters. Now, what we're doing in this particular chapter of the presentation is treating a simulation of this ring over just one turn, one revolution in its lattice, and examining the central dynamics of that particular device. Now, this is an elementary test problem because there exists a first principles model we can compare our results to, and also there are prior results using machine learning that we can compare our results to. And what we're doing is leveraging a well-validated and verified code called warp to produce virtual data along just one turn. We're producing virtual data and not using experimental data because there is a sparsity of data points we can take the experimental data in. There's only 15 or so beam position monitors, which tells you the location of the centroid of the beam, located at discrete points along the ring. And that just doesn't provide enough data, just one turn. And so what we're doing is taking basically a cross-sectional slice of an electron swarm as it goes around this ring. Now, what's an electron swarm look like in this thing? So the image I'm showing you here at the bottom is the output of the code called warp in a different lattice. And what you can see here are a bunch of colors. The electron beam is the yellow and the green quantity here. What you can see is this clustered swarm of particles. The green color corresponds to high axial kinetic energy. It's going very fast down the beam pipe, shown in gray. And the yellow corresponds to low axial kinetic energy. The axial kinetic energy in these guys is shown in dz, that's velocity, and the perpendicular transverse thermal velocity of these electron swarm is much less than its axial velocity. The radius of our beam pipe, inner radius, is 25.4 millimeters. And because this particular electron swarm is, it's made of electrons, there are many particles in it that won't blow each other apart. These electrons, they have the same charge, they don't like each other. So in order to constrain their motion, we use the static magnetic fields to massage the electron beam and make sure it's not blowing itself apart as it's going along the lattice. And we bend the electron beam with dipoles, which produce just an electric field from one point to another point of a straight line. And thus, if you hit a charged particle, it goes the opposite for an electron for the field lines. And that bends the electron beam in a discrete ring. So this particular research lies underneath the umbrella of one of the grand challenges in my field of accelerator physics. As I mentioned before, beam prediction. This grand challenge poses the question how do we develop predictive virtual particle accelerators? So accelerators have a variety of applications, two of which are fundamental research, for example, at a Large Hadron Collider at CERN, which is a research facility which has an proton beam collider, which is 30 kilometers in circumference, and accelerates proton beams to 0.9999 C. And the object of that research is to collide those proton beams together and create beams that are both targeted and bright. So by targeted, I mean they're going to a particular point, particular location. And by bright, I mean there's a high electron fluence per area. So it's a very small spot size. So if you have a laser pointer, for example, like here, high fluence would be a very bright laser pointer versus one that's very diffuse and spread out over space. Another application, which is dissimilar to the fundamental research performed at the Large Hadron Collider, which is a 30-kilometer in circumference ring, is an electron microscope, which accelerates electrons to very small energies. Not small, but only tens of keV instead of GeV or even greater at the Large Hadron Collider. And these electron microscopes, instead of propagating over a distance of many tens of kilometers for many, many turns in the Large Hadron Collider, for example, they are only propagating over a distance of a meter or so, if that. Traditional approaches to capturing the complex dynamics associated with these these beams in these systems are either computationally expensive first principle simulations, so simulating all the dynamics of all the particles in a beam, for example, interacting together, or black box machine learning. And by black box, I refer to the notion that you don't understand exactly how or why it works. It just kind of works after you train it right. So our approach, we seek in our approach to thread the needle of these two particular approaches that I showed you before. And it's a novel application of a technique from the data-driven nonlinear dynamics community called SINDY, which stands for the Sparse Identification of Nonlinear Dynamics. So how does SINDY work? It finds minimal descriptions of complex evolution, and it can be used to uncover physics and problems that cannot be solved analytically. And it also uses user-generated basis functions. Instead of machine learning, which just uses an arbitrary set of basis functions for all the particular objects that are contained within this network, SINDY works by allowing us to project the complex ensemble dynamics in this particular research onto user-selected basis functions, which I will enumerate in a moment. So one assumes a state variable x, which lives in some n-dimensional state space. And then one assumes that x evolves as a function of time, or for us along the lattice in z, as a system of coupled first-order autonomous ODEs. And what I mean by autonomous is that the independent variable z here does not show up in this f of x here on the right-hand side. One then measures in either simulation or experiment the state variable x, which then composes that data a capital matrix X, which has a number of columns in a matrix associated with the number of state variables. For us, that's 3, and I'll enumerate those state variables in a moment. We then have a number of time entries associated with the data collection associated with that particular device. And then one equates capital X dot to f of x, which is then composed of a theta matrix, which is a library of basis functions, which is a function of state variable x data, and then a matrix xi, which is a matrix containing all the coefficients that SINDY seeks to learn, which multiply the basis functions. These basis functions here, we have 28 of them, and I'll enumerate them in a moment and how we selected them, can be constants, they can be polynomials, they can be trigonometric functions, sine and cosine, or whatever the user selects, based on either first principles physics or intuition. This data matrix multiplies the xi matrix, and the object, as I mentioned before, of SINDY is to find these coefficients that multiply these functions that we can then interpret the results of the research that we're doing. So we then, so how do you go about selecting these basis functions? Hi, Tom.
Sorry.
So the plot I'm showing you here in the bottom left of this slide is of the beam centroid rattling around the University of Maryland electron ring over just one turn. And it's basically the result of us unwinding the accelerator and looking down at like a telescope, like as if we're pirates, and then looking at the result of that beam centroid motion rattling around in there from us realistically misinjecting the beam in our allometry test problem. We misinjected the beam by just 1 millimeter. You can see the starting point just barely here on this plot in both the X and the Y directions. So this plot is showing the horizontal centroid motion on the horizontal axis in units of millimeters and the vertical centroid motion on units of millimeters on the vertical axis. And it's kind of notionally kind of like a harmonic oscillator going around in a circle. It's doing some circly stuff. But one key thing here is that we can't just learn this motion because it's not autonomous. And then the reason that we know that is because this plot is self-intersecting. Not every single point in state space is unique. So in order to enforce this equation to be autonomous, we unslinkify it and we introduce as an additional dependent variable, we cheat basically, and we introduce the independent variable z as an additional dependent variable in our differential system that we're learning. And the result of that looks like this. So we thus now have added z as this axis here, and our state variable x is now z horizontal motion xc and in the vertical centroid motion yc, which we assume evolves a system of coupled first order autonomous ODEs. And we also know the first terms we wish to insert into how f of I evolves, which is our harmonic oscillator. We also use, based solely on data, the power spectra to populate the rest of how f of I is. And I'm showing you here on the right now the power spectra for both the horizontal and vertical centroid motion. The horizontal motion is shown in solid blue, and the vertical is shown in dashed yellow, with the k to the -4 trend line shown here. The horizontal axis of this plot is the axial wave number associated with the motion that's going around the ring. And the vertical axis is the power spectra shown in units of meters squared. So based solely on data, we naively assume the first 3 peaks of this power spectra correspond to periodic forcing, which we assume come from the magnets of the accelerator. We then also insert a nonlinear interaction term, which we assume comes from these cascading pairs of peaks as we go down in the power spectra. The first 3 peaks of the power spectra are tabulated here, and these values for these axial wave numbers and their corresponding lengths are inserted directly into SINDI. And the object of SINDI is to learn the coefficients of each of these terms so that they can be interpreted. And this is in contrast to both first principles simulation, which is a complex simulation, which results in a large data set. It can be very expensive to produce and analyze. And also machine learning, which is non-interpretable because every single one of the basis functions in machine learning and typical approaches, you can't understand why exactly that's working. So how does SINDI do? So our SINDI fit compares favorably to both the data and also a first principles centroid model. The centroid model is shown here at the top right of the slide, where you have 2 second order non-autonomous ODEs. And these equations here have 2 terms, which come directly from the first principle simulation and that are directly injected into this model. The first term here, kappa x, is associated with the quadrupoles, and that is the focusing which constrains the motion, both x and y. They have opposite signs for the horizontal and vertical centroid components because quadrupole field structure. And we also have the dipole term here, which bends the beam around in the horizontal direction and closes the full loop, basically. And so the SINDI fit does not have knowledge of the explicit structure of the magnet model at all. And you can see the results of the warp data shown here on this power spectra plot again for the horizontal centroid motion shown in the blue, and SINDI fit in the orange squares, and the centroid model shown in the green diamonds. You can see how the SINDI fit accurately recaptures the first 3 modes fairly well, but it doesn't capture anything else associated with power spectra because we did not directly inject high, longer wave number and shorter wavelength physics into the model that Cindy was learning. In contrast, the centroid model captures these higher order dynamics, but doesn't quite capture the other structures that appear, that present themselves within this power spectrum. So we can interpret the results of Cindy in the context of this first principle centroid model. And we can show that while the centroid model outperforms in this particular case, we are attacking this elementary test problem because we can compare it to a centroid model. And in many of the environments that Cindy can be used in, analytic models are either insufficient, for example, they cannot capture these dynamics, or they don't exist whatsoever. And so what we seek to do in this particular case here is show that Cindy, using only data and not knowledge from a first principles model, can capture much of the dynamics associated with the particular physics of this device. So how does Cindy compare to machine learning? So there are 4,000 neurons in this other machine learning technique, reservoir computing, that was used by my colleague several years ago. And we compared that to the results of our three-dimensional first order system of equations that Cindy learned. So I'll be showing you the results of the centroid motion, shown not just over learning the dynamics data shown for one term, but subsequent terms in prediction. So the top row I'm showing you here are the results of the Cindy model, shown for the horizontal motion on the left and the vertical motion on the right, where those vertical axes for both of these plots are shown in units of millimeters, and the horizontal axes are the axial locations of the beam that's going around for turn 2 and turn 3 between 11 and 24 meters and 24 and 35 meters or so. Simulation data for both these plots from the warp simulation is shown in blue, and Cindy fit is shown in orange. You can see that for over the first turn subsequent to training, that the Cindy fit captures the dynamics associated with the data fairly well. However, as you go to the third turn, which is one turn more than the data was actually trained on, you can observe that for the horizontal centroid motion, there's an amplitude offset which is introduced, and a smearing out of the higher order frequency behavior. However, for the vertical centroid motion, Cindy fit captures dynamics fairly well. Now, this alternative machine learning technique, reservoir computing, that my colleague performed, was trained on the same data that we presented to Cindy. And that's actually the other reason we also chose this problem, because we could do an apples to apples comparison in terms of the training data that Cindy, that both these techniques were presented with. Now, the results of this are shown similarly to above for the Cindy technique, where you have the horizontal motion for the centroid on the left and the vertical motion on the right. And the horizontal axes for both these plots are turns 2 and turns 3 respectively, with the black line denoting the difference between turn 2 and turn 3. You can observe that for turn 2 again, that this motion is particularly captured well. However, as you go to turn 3, the horizontal motion is captured, but the vertical motion is not so much. The fidelity of the data set looks qualitatively the same, but there's a frequency shift that's introduced. And the dynamics associated with this machine learning technique are slowing down relative to the dynamics of the data. So in summary, in this particular chapter of my presentation, I've demonstrated methodology to capture realistic beam dynamics in an elementary test problem with both the first principles model and the Cindy fit. I've also reduced computational cost and complexity. The simulations in warp, which were used to produce the data, took about 15 seconds a turn to run, and that's on a compiled Fortran code on a Linux box. Now, is in contrast to the Cindy equations, which took less than 1 second per turn to run on a simple Python integrator, which is a dead simple integrator for interpreted code. I've also obtained a favorable comparison to machine learning using 4,000 neurons versus a three-dimensional ODE. So depending upon one's needs, one could choose to use an interpretable technique like Cindy with user-selected basis functions that learns the coefficients, which can then be interpreted based upon first principles models, which may not be always available or sufficient to capture the dynamics of what's going on, or a black box machine learning technique that you don't know how or why it works. So this summarizes the second chapter of my presentation. Before I go on to the next chapter of my presentation, I'd like to ask the audience a question. How many of you guys have experienced allergies the last couple weeks with all the pollen coming in? A fair number. So hope not to offend you with the next slide I present on. So this image here I'm showing you is of pollen grains, which may be the culprit for your allergies. But it looks awfully small, doesn't it, on the slide? Let's zoom in. Let's use a microscope. There are two particular pollen grains I'd like to draw your attention to in this plot. This is an image taken with a scanning electron microscope. The pollen grain for this particular object here is the morning glory pollen grain. Pollen grain with this image here of this pollen grain is the sunflower pollen grain. And they look awfully similar. And so depending on the qualities of the electron beam that was used to image this particular device, if there are aberrations, for example, in that electron beam that were not calibrated out or well understood, one could perhaps misidentify the morning glory as sunflower or vice versa in this particular image. And so there is knowledge of and control over the distribution function, and in the case of aberrations excessively, is important so that one can take data or images like for example, on this electron microscope, such that you can actually trust the results of your experiment that you're performing or your actual microscope. Do you have a question, Chris?
No.
Oh. So this particular research here that I'll present to you in this chapter lies underneath another one of the grand challenges of my field of accelerator physics, and that's beam control. How do you measure and control the beam distribution such that if aberrations were present in an electron beam that was used to take an image, you could factor that in to the data that was taken, such that you would not thus misidentify objects in an image that are very similar to each other. So these aberrations, as I mentioned, can cause misidentification. And these aberrations are a structure in the phase space of an electron beam, which recall is the space spanned by all the positions and momenta or velocities of all the particles in that electron beam or swarm of charged particles. These phase space structures damp out, they only wash out in phase space on a timescale that is intrinsic to the electron beam. They do not wash out on a timescale associated with externally applied focusing at all. And so we seek to understand and control a beam distribution in this particular presentation in the simplest experiment available to us at the University of Maryland Electron Ring, at the University of Maryland. And so to do that, we are analyzing the dynamics of an electron beam as it propagates in a linear accelerator. This electron beam is produced by a gridded cathode and an electron gun, which accelerates electrons up to some significant fraction of the speed of light. It's around 0.15 c or so, which corresponds to 5 keV electrons. We then aperture part of the beam. We don't use the entire beam produced by the electron gun. And which we then focus with a solenoid located at 12 centimeters or so from the aperture plate, which we assume for all simulations and experiments and theory to be at location 0. We then measure the beam currents with this blue quantity, the current transformer, and there's an additional solenoid which can be used in further experiments or simulations, but we turn off to be 0 in this particular experiment. We just want to use the simplest focusing system possible to understand the beam dynamics, so we can gain knowledge of the whole entire phase space distribution for this electron beam. We then image the beam with a sliding phosphor screen shown here, which we move axially up and down the beam line in order to image the configuration space, the XY space of the beam, which is only one of the 6 unique transverse space projections of the 4D transverse space, which is the position in X, velocity in X, position in Y, velocity in Y. Those entries correspond, if you multiply the 2x2 matrix of that together, a 4x4 matrix, I should say, that corresponds to 16 entries, 4 of which are trivial, and you just only have 12 remaining, which corresponds to the up diagonal and lower diagonal. The up diagonal are the unique phase-space projections of 6 unique phase-space projections of the 4D transverse phase space, of which we only image one with this screen here, which you then analyze on data with a camera and analyze on a laptop. So what's the data look like? So what I'm showing you here is a plot of the beam radius on the vertical axis, and the horizontal axis here being the axial location that we take the data from. This first location here is of the closest the location we can most closely approach the aperture plate without damaging the experiment. The data is shown here in the black circles with a systemic error shown in an opaque gray area superimposed on the black circles, which comes from 3 sources: the sliding phosphorus screen, which we controlled with a hand, and just moved literally with the hand and measured the location with a meter stick, so that corresponds to thus an amount of error. We also had error coming from the resolution of the camera, and also the way we calculate the beam radius. So at each of these locations that are shown here for the beam radius, we image the beam in configuration space. At the location of closest approach, right here, you can see the beam being fairly small. Each of these plots here that we'll be showing you is of the beam from -10 to 10 millimeters and both the horizontal and vertical axes or so. The blue color corresponds to low pixel intensity, which is a proxy measure for electron beam number density. And the yellow here corresponds to a very bright part of the beam, which is high pixel intensity and thus high electron number density. The white horizontal and white vertical lines correspond to either the column sums or the row sums for all the data shown in that particular plot. Now, as the beam propagates downstream, it expands. And you can see here how much larger the beam has gotten at this particular location, and also how non-uniform it is. As it's focused by the solenoid, recall located like right around here or so, the beam size gets smaller and other structures start to present themselves in the particular configuration space that we are imaging. Namely, like these 4 peaks here at the edges, which turn out to be the forerunners of a ring wave, which propagate radially inward. Now, as this ring wave propagates inward and the beam starts to expand outward radially again, another structure presents itself, which has quadrilateral symmetry here, and which we named the cruciform. At the last location, the ring wave has now impacted the origin, and the cruciform is readily visible at the end of the experimental data set. What we seek to do in simulation is to capture this behavior so that we understand the phase-space dynamics. We know we understand the phase-space dynamics of this beam, and thus that simulation can then be used for other research utilizing this electron beam. Now, these features, which we see here in this particular distribution, manifest from both a cathode grid, which imprints this cruciform structure on the electron beam at birth, and also the nonlinear solenoid field, which forms this, which creates this ring wave propagating toward the origin after the beam interacts with the solenoid. So, how do IE simulations initialize with ideal distributions attempt to capture or compare to the experimental data? So what I'll be showing you in this particular slide is a movie comparing the results of experimental data shown here on the left, with the vertical axis being the y location of the experimental data shown in units of millimeters from -10 to 10, and the same being true for the horizontal axis, and 2 simulations initialized with either a uniform distribution in configuration space and a thermal distribution, a Gaussian distribution in velocity space, or a beam initialized with uniform distributions in all projections of its phase space. So it has its uniform beam in configuration space and also a uniform beam in velocity space as well. So as I play this movie for you, you will note that while the simulation middle, which we denote the semi-Gaussian distribution, captures the appearance of the ring wave, it does not capture the associated cruciform structure as it, I'll play this movie at the end right there. It does not capture the speed of that ring wave, nor the cruciform structure. In contrast, the simulation here on the right does not capture any of the structure associated with either the distribution, either with the ring wave or the cruciform structure. And so what we seek to do in this chapter here is capture the actual structure, but in order to do that, we have to understand the entire phase space of the beam in an experiment. And one way we can capture that is by using a pinhole scan, which is done by imaging only one tiny little point on the beam in configuration space and allowing that point and then imaging the results of that point at a particular location further downstream. So the full beam comes in, and we only look at a teeny little bit of it, and then image the resulting beam as it expands outward. And that gives a measure of the beam's velocity space at that particular point. Now, if one were to raster this pinhole over the entire configuration space of the beam, one could then gain knowledge of the entire phase space, all the positions and all the velocities of every single point in the electron beam. Now, we assume in our experiment that the beam is azimuthally symmetric. So if we were to advance across only radially in one line, we gain information of the beam's velocity space at every single point, also in configuration space. And after measuring this transverse velocity space, we obtain this data, which is shown here in the bottom left of the slide, where I'm plotting a dimensionless velocity in the x direction and dimensionless velocity in the y direction on both the horizontal and vertical axes. This dimensionless velocity here is the result of the transverse velocity being divided by the axial velocity, which is much greater than the transverse velocity, which is why this is in units of millirad, which is an angle unit. And that's why these values are very small, 10 millirad, 20 millirad. So this particular distribution does not have an analytic form. It is totally empirical. And so we treat it as a probability distribution, which we then sample from in order to initialize the entire phase space of a distribution in our simulation. And we actually, in part, imprint this on the phase space of the beam in our simulation, the result of which I'll show you now. In this slide, I'll show you the results of comparing a first principles model, which is a second order ordinary differential equation, shown here on the left, which has three terms. This particular equation involves the beam radius as a function of z. You have a focusing term here, which is associated with the solenoid. You have defocusing terms here associated with the charge repulsion of all the particles in the beam, which is associated with the electrostatic repulsion, right? And you also have a term here, epsilon, which is a measure of the size of the beam in phase space. If the beam has more transverse velocity, if there's a higher transverse velocity, it has a greater area in phase space, and because that transverse velocity is kind of like a temperature, it thus has more random motion and thus expands outward more. So the result of a first principles model and experiment and the result of the beam radius of our simulation are shown here in the bottom left of the slide, where we have the experiment replicated from 2 slides ago, shown in the black circles with the error bar. We also have the model shown in the solid blue and the simulation in the dashed orange, which is shown here on this plot. We also have a dotted purple line corresponding to this a notional representation of the focusing function of the solenoid here, which focuses the beam down to a beam waist before it expands outward. Now, the model and simulation and experiment all agree fairly well up until the end of the data set, which we speculate comes from either optical or mechanical misalignment of our system, or a steering dipole, which is a device we use to steer the beam. And I showed in my dissertation that the use of this dipole here induces a change in beam radius of around 5%, and also qualitatively changes the beam structure as well. And so while the model can capture the beam radius, it cannot capture any of the structure. And the movie I'm about to show you is the result of a comparison between the experiment using the same axes as before, shown on the left, and a simulation utilizing the pinhole scan from the prior slide to initialize the entire phase space of the electron beam. And I note the simulation pinhole pH. You can observe in this simulation that both the ring wave, which it forms at the appropriate location and has the right velocity, and also the cruciform is captured in this simulation. So in summary, in this particular chapter, I've shown that a simple model can obtain the beam radius, but cannot replicate beam structure. And other simulations with ideal phase space distributions also cannot replicate beam structure. And a result, and a direct comparison of all the simulations shown here at the bottom of this slide, where we have the experimental data on the left, shown at the last location we took data for. The result of the pinhole simulation, shown here in the center left. Center right being the result of the semi-Gaussian simulation. Recall that was initialized with a thermal velocity distribution. And the KV simulation, which was initialized with uniform velocity and configuration space distribution. You can note that as you go from right to left, the KV distribution does not have any features or structure in it whatsoever. The semi-Gaussian has the ring wave, but it doesn't approximate the right location of the ring wave at this experimental data location. The pinhole scan here captures both the ring wave and its location as a function of time, and also cruciform, which is represented also in the experimental data. So this validated pinhole simulation is now usable to investigate beam dynamics further downstream that can be used to either extract or suppress features and understand any aberrations like this cruciform or the ring wave. So in summary, in this presentation, I've shown how one can use either measurement or data-driven modeling and simulation to obtain higher fidelity. I showed this in chapters 1 and 3. Lower computational costs. I showed this in chapters 1 and 2. Achieve interpretability. I showed this in chapter 2. And advance expensive design or explore the dynamics for devices such as ASICs or accelerators. I showed this in all the chapters of this presentation. Potential future work of this research could be to improve our one-dimensional stochastic differential equation model for capturing the statistics of the tunnel junctions, and include higher order behavior in it that can then be used to model n-body interaction of all these tunnel junctions. Because recall, we only modeled the dynamics of one tunnel junction, and we did not model the dynamics of many tunnel junctions interacting together, because that's what would actually be used in order to solve a computational problem that is mappable to Ising spins. We can also extend the SIND model to the full phase space and not just analyze the dynamics of the centroid motion or centroid location, but the centroid slope or its velocity. And we can also examine experimental turn-by-turn behavior in a Euler lattice, and not just use virtual data over one turn, which allows us to collect many data points, but also experimental data at sparse locations along the electron ring. We can also, in the last chapter, investigate length scales and mechanisms over which the features we observe, namely the cruciform and the ring wave, homogenize in phase space. I'd like to also thank, in this presentation, all the individuals who are shown here on the slide, many of which are in this room, that helped enable this work, and without whom I would not have been able to do it.